Let's start our journey over 2000 years ago with the Antikythera, the first known computer. Ancient Greeks built this remarkable device to understand the motion of celestial bodies. Fast forward to the 19th century, we meet Charles Babbage, who developed the analytical engine, which was geared for engineering problems. But the real revolution came with Alan Turing, the pioneer of computer science. After working on Colossus, the first digital programmable computer, Turing formulated the theoretical basis of all classical computers we use today. Turing had a brilliant insight. He imagined an infinitely long tape divided into squares or cells. Each cell could contain a 0, a 1, or remain blank. A processor would read this tape and perform just 6 operations. Read the number in a square, write a number in a square, move 1 square to the left, move 1 square to the right, change the number in a square, or stop. Believe it or not, every classical computer today, your smartwatch, your smartphone, even self-driving car, is fundamentally a Turing machine. These machines use binary language instead of our familiar base 10 system. So the number 1 is represented as 1, 2 as 1, 0, 3 as 1, 1, 4 as 1, 0, 0, and so on. Let me show you a simple example. How would you perform a calculation 2 plus 2 on a Turing machine? We start with the input 0, 1, 0, which represents 2 in binary. The processor moves to the middle cell containing 1 and replaces it with 0. Then it moves 1 step left to the 0 and replaces it with 1. The tape now reads 1, 0, 0, which equals 4. That's addition on a Turing machine. Numbers are stored in memory, processed, and the final result emerges as output. Now, here's where things get interesting and frustrating at the same time. Despite the revolutionary invention of the transistor and decades of following Moore's law, we've reached problems that classical computers simply cannot solve. Even our biggest supercomputers lack the computational power needed. We have successfully simulated simple systems like hydrogen atom, which is an 1 electron atom, but larger molecules, that's where we hit a wall. Let me give you a real world example that affects every single one of us. Nitrogen fixation. Nitrogen makes up 78% of our atmosphere, yet it is unusable in its natural form. All plant life, and by extension, all human agriculture, depends on fixing this nitrogen into a usable form. Nature accomplishes this through 2 methods: lightning or specialized bacteria using an enzyme called nitrogenase. The magic happens in something called the iron-molybdenum-cofactor. This is a complex cluster that serves as a catalytic center. It is this remarkable metallic cluster that breaks one of the strongest bonds in all of chemistry, the nitrogen triple bond. Bacteria like Rhizobium in legume roots or Azotobacter and Cyanobacteria perform this effortlessly at room temperature. But here's the kicker. Despite decades of research, we still don't understand how nitrogenase breaks this bond. Why? Because simulating the iron-molybdenum-cofactor on a classical computer would take billions of years, longer than the age of the universe. Because we can't simulate this natural process, we rely on artificial fertilizers produced through the Haber-Bosch process. This process is incredibly energy hungry and contributes significantly to global warming. Meanwhile, bacteria do the same thing at room temperature using a mechanism we cannot even model. The computational limitations extend beyond material science and chemistry. Consider the max-cut problem from graph theory. This mathematical problem maps directly to real-world applications like delivery, route planning, portfolio optimization, as well as network reliability. These are problems that businesses face every day, yet they are computationally intractable on classical computers. Here's the good news. Later in this course, we will tackle some of these optimization problems using real quantum computers. You will get the hands-on experience with technology that can potentially solve what classical computers cannot. But first, we need to understand how quantum systems actually work. That's where we are headed next.